And they gave them loans from the university.
Yes.
What inventive. What did they do with this deal? Out of the, yeah.
Okay. Think we're gonna start. Think we were missing a few, but it's our time now. So unfortunately, oh, this is working. Great. They'll have a bigger challenge later to understand what I'm saying in this lecture. So first of all, if there's any huge answers, questions, or misunderstanding about yesterday, I don't think so that something was extremely um, hard yesterday, right? Great. So okay, so today we have a few topics that we want to discuss, and I will start again with a disclaimer. So there is a lot of theoretical work at the things that we're going to talk about. So the first part will be general speaking about random processes. And if that stops, please tell me. Okay? Yeah, I think it stopped. Hey. Okay. Just let me know if you stop hearing me. So we're going to discuss today, we're going to start about random processes, and later on we're going to discuss some SST issues. Yeah, this is broken. Can, no, the battery is up. Can any one of you handle this? Great. Thanks. Okay, so I guess, my guess is that it's not very clear the relationship between random processes and SST or Fourier transform or any talk about frequency decomposition of signals. So I want to make it clear now, and probably going to ask a lot of times, why do we do this? And I will say the same thing, that first of it, we just want to describe a little bit about random processes. What is a random process, and what is the properties of it? And my main issue of this part will be to show you some properties to give you some feeling and some intuitive about how we can look at data. Sometimes how we can look at different properties. Sometimes maybe somehow similar to what we did yesterday, but there is a step that is connecting between random processes and SST. I'm not sure we're going to get into all of the details, but you have all the slides. I already uploaded them yesterday, and I have the benefit that thank you that I want to finish this part a little bit faster than usual, and I don't want to get inside all the details. Uh, and I again have the benefit because I think you're well educated and you have the potential to read furthermore by yourself, and maybe because of this we'll get to know a new material tomorrow and not get stuck only at these properties. So the first thing that I said about random processes is that I want you to get some feeling about it. And the second thing was that there is some connection, and probably I'm not going into all of the details. And the third part is that a lot of times data that we collect might seem as a random process. Okay? So when we'll see a real data, then we can start to think about it. What are the parts of the data that are random, that looks like random processes, and can we get rid of them, or should we get rid of them, or not? So I'm going to probably say it a couple more times, but
This is the main agenda for us today. Okay. Hey, I think this is, the microphone has died again. No, no. So random processes. Again, disclaimer. Most of the material of this course was taken from Eli Nelkin, and when he prepared the original slides, he had some prerequisites about your knowledge about statistical methods. So I'm not taking under the account that you know everything, but you should know all the stuff that I'm going to show you in order to learn by yourselves from the slides all the rest of the material that I won't cover. So I added these were the prerequisites, but I think eventually, maybe not now and maybe not next week or not for our part of the course, you should at least know what all of these words are saying and maybe read extra about them. So I'm gonna just read them pretty fast. So Eli assumed that you know what is a random variable, what is the distribution of random variable, probability density function, cumulative probability function, common distribution, uniform, binomial, Gaussian, and Poisson, the concept of statistical independence. This is also were prerequisite. Expected values, mean, median, mode, variances, standard deviant, covariance, correlation coefficient that we talked a little bit yesterday. So eventually, until the end of your PhD, this should be fully mastered. You need to be you need to calculate them by hand, etc., etc. Linear regression can be also a nice idea to have some notion with it. And again, probability theory, which you will see in other courses. Okay. So yeah, of course, classical central limit theorem. I think most of the courses in the ICNC should assume that you know it, and also the laws of large numbers. Okay, so let's start with some notion about random processes, just to give us some feeling. Does anyone has an idea what is a random process? I think it has a unique name. It's random process, random in time. Any ideas? Okay.
It's a sequence of random variables.
Okay. And we want to somehow describe it in a more statistical fashion. Okay, it has some distribution, and it can also have some interesting parameters, like the mean, like the variance, like the dynamics in time. Yes?
Stochastic process and random process is the same?
No, no. These are not the same, and we will look into it. Okay. Okay. So I'm going to generate some processes, okay, and 3 processes that look like this. Okay, so those of you who read the code can see that I'm using a random function here with some distribution. And there are 3 graphs here, 3 plots. The upper plot, which seems like a process. We still don't know what's exactly going on there. The second one and the third one. So let's try to just describe it graphically as we did yesterday. So we see that you can see. Okay, I think this is better. So yesterday we talked a lot about the modulation in the signal, okay, and the connection between the modulation to the width of the line. So we can see that in the upper panel there is something that looks like it's going up linearly, okay, and there is some fluctuation, and maybe we can understand something from the width of the lines there. Okay, for first it seems like this line is a little bit more smooth, okay, and there is less fluctuation here. There's more fluctuation here. Let's run the same lines again, and I will generate more or less the same thing. Okay, and we can see that again the three graphs still has more or less the same shape. If we look into the details, we can see that everything looks totally different, but there is still a main shape that is governing the three plots. Okay, if you read the code, I'm guessing you can't read very well the code, which is okay because I gave you the code and you can run it later. And I'm gonna hold the plot and I'm gonna plot it again and again. Okay, so I added another one and another one, another one. Okay, so I think by now you can start imagining that even though I ran the same random process and the same function build this sample, after a few times as I build this one, we can definitely see better the linearity of the signal. And here, again, we can see that there is some shape, but for every instance, most of the dots are not on top of each other. And the same thing here. So, does anybody has any idea what are the functions that underlying these three? So this is easy. This looks like a smile. What is a smile? Parabola, right? A second order, and this one. Okay, it could be a third order, it could be 5 or more or whatever. In the code you will see that this is linear, this is a positive parabola, and this is in order of 5. But still we can see exactly what I just said, that from one instance it was hard. When we repeat the same random process, we could see the underlying mechanism. We could imagine at least the underlying, and when we average it a lot of time, we could see much better the function that was beneath it. Okay, now let's check some properties of this signal, exactly as we did yesterday. Okay, so I'm gonna plot this signal. Oh wait, sorry. I wanted to start without the hold. Okay, so again, clear the plot, and okay. So I just run it 100 or 1,000 or 10,000 times, the same random process, and it's the same, almost the same one that we just saw in the upper panel, which is linear. Okay, so there is a progression in time, and we can see that the values fluctuate a lot. Okay, we still don't know what's the correlation between them, but a few others, very simple stuff that we can see is it's the variance of the whole signal. So if you look at the beginning of it, it seems like it always starts in the minus part. It has some limitation in the minus part, okay, and it develops during the time, and the same thing in the last point. So there is some variability that is changing across time. So now we're going to ask what's going to be the probability of all of these lines, and we're going to look at the first point, only at the first point, at all of the lines, and we're going to ask how many of them do you think are going to be under -3 for the first point? Okay, so of course we could compute it because we know how we made the sample. But can you guess if I have 10,000 of these samples, of these lines, and every line is linear from -1 to 1, and you could have guessed already that I added some random noise, and the random noise was with some sort of variance. So just want to give you a feeling before we actually look at it. So now I'm going to hold the plot. I'm going to plot a lot of them. Okay. This is probably enough. So you can see that you can actually see the variance, and now we're going to ask what the probability for the fourth point to be -3 and for the last point to be above 3. So we can do it also in MATLAB. So this line, I'm going to read it if you can see very well. I'm going to find all the samples that in the first point, so this represents the first point, the two dots represent all the 10,000 samples that I had in my matrix. I'm going to find all the points that the first point was less than -3, and the last sample, which is 128, is bigger than 3. And the answer is here. Okay, it's 250. Okay, which can be surprising or not. Okay, I think intuitively, because the variance, the lower boundary of the variance here is -3, and again the upper variance of the last point it's around 3. We couldn't really guess how many of them start beneath it and end above it, but we can do it with MATLAB. And let's see how many of them are about average. So what is average? The first point is starting with around -2. At the beginning, at the middle sample, at 64, it's going to be above -1. And in the end, sorry, in the middle, we're going to check if it's above -1 and beneath 1. So it's going to be here. And in the end, it's going to be less than 2. So intuitively, you're going to say that, I don't know, many, okay, because it's the same random process, and it's 2,000. So it's fifth of the number of all of the initial samples that we ran. And let's finish with how many of them has the maximum of bigger than 5. So it's 128 outside of 10,000. And just show you some basic properties about randomness in the samples that I did. But everything here was to give you intuitive about actually a random process with a Gaussian distribution. So if we have any Gaussian distribution, all the questions that I just asked you, what is the probability of, or how many of the signals is beneath some sort of a number, if we knew the probability distribution function, we actually could have just compute it and not count it. Okay? So this I'm not going to talk exactly about how to do it, but I'm guessing that you know how to calculate with a density function what is the probability of my signal to be here, or here, or here, or both. So here I did it with MATLAB, and I calculated the probability of the first thing that we calculated. What is the probability to be under -3 at the first point and above 3 at the last point? And the probability is extremely low, which is 0.02. But if we'll take 0.02, we take the answer and we multiply it by the number of all samples, we have exactly 252, which is more or less the number that we counted. Okay, so that gives us some intuition about Gaussian distribution and random processes, and we're going to talk a lot about them. Okay, so Ellie has a lot of to be pedantic slides, and you can definitely read them and ask me later about them. And so I'm going to do it quite fast. A random process is defined by its finite dimensional distribution or the probability of events at a finite number of time points. A stationary process is a process with statistical properties do not depend on the choice of origin. Okay, we saw that actually yesterday also. And the distribution of individual samples is independent of where you look at them. We'll see it in a second. The joint distribution of pair samples depends only on the time interval between them, exactly as we did yesterday. We chose some interval of points, and it doesn't matter where we started the point. The distribution was the same, and so on and so on. So stationary, we already has some feeling about it. Ergodicity, I let you read it later on. And okay, the additive model of data. So here we saw a data that was built from some function. It could have been a signal. So the data is composed of a signal which is identical from repeat the experiment of each other experiment. And we can add to the signal a stationary noise. And as we said yesterday, the noise can be assumed most of the time to be Gaussian. And as we said yesterday, why Gaussian? Why we said Gaussian yesterday? Because it is written. Yes, it's simple. It's an analytically trackable model. We can describe it. We can show that the noise is Gaussian, and with other statistical rules such as central limit theorem, we can actually assume something and get results. Okay. So now let's look more carefully at some properties of Gaussian processes. So again, we have the more or less the same process. And now let's do what you actually all really wanted me to do, but I wanted to do it now. Let's look at the distribution of the first point. Okay. So what we have here? We have 10,000 traces of what we just saw that was running on the screen. And instead of looking at all of these processes, I'm looking only at the first point of the line. And I'm looking at all the first points in all of the samples. And here is the histogram distribution of the first point. Okay. So we can see that it has Gaussian shape with some variance. Okay. So again, most of the points will fall of the first point will be around -2 with some statistical distribution around it of -1 or -2, and some of the points will be in -4, -5, or at the other part, just as we computed and searched for it in the signal. But once we also want to show that it has some stationary properties. So what I'm going to do now is actually, instead of looking only at the first point, I'm going to look at a few other points. So this is exactly the plot that we just saw. The histogram of the first point on all the 10,000 samples, sorry. This is the histogram of the 32th point in all of the samples. Okay, so it's still Gaussian, and we can look at all of the points in all of different times. So this is the first point, this is the end point, and some in the middle, and they all had these Gaussian properties with almost the same shape, almost exactly the same variances and other parameters. So it seems like this process was stationary, right? Because it keeps the same properties in time.
Why does the mean change?
Okay, the mean is changing because let's see again at the process.
So why do you call it stationary if the mean change?
Okay, so this is the random process. Okay, I didn't say that it could have had any other meaningful parameters. As we saw at the beginning, we looked at 3 different random processes with some shape beneath it, okay, and it could have some interesting parameters. Here, the parameter is that there is linearity, but except the linearity, everything is random. Okay? And as we said, in additive models, we can have a signal which is not totally random, and we add above the signal a noise. Noise is random. And when we look at the mean, we can see that this signal has some properties in time about the mean. So this is interesting. What is less interesting is the noise. But we saw that the noise is stationary and Gaussian. How we saw it without looking at the mean, we just look at the distribution of each point, and in each point in time, we saw that the distribution is Gaussian. Okay, so this is the reason why the mean is going up. So these are all the points, and this is the mean over time. Okay, and this is the variance over time. So we can see that the mean is exactly the linear function that was underneath what composed this signal, and the variance is, it seems like it fluctuates a lot, but actually everything here is around 1. I don't know if you can really see it, but this is 1.05, this is 0.95, and everything is really around 1. So we have some descriptions about this random process in time, and we saw that it says stationary and Gaussian. Now let's see what else we can do here. Okay, I'm going to take a different process now. Okay. So in the left panel, we see the same random process that we just looked at, and here something a little bit different is happening. Okay, so let's do the same exercise. What do you think the difference between them? Because you can't read the code, it's great, because now you should guess.
I think more samples.
More samples. No, so they both have the same amount of samples. It starts with 0, it ends around 140.
The one on the right could be non-stationary.
Okay, it could be non-stationary. For this we need to check all the parameters.
Both are not stationary.
Both are not stationary. So the first one we saw is stationary.
If between 0 and 60, the average, the mean is not the same from 60 to 120. It's totally different.
So again, to see that it's stationary, we looked at a lot of different points. Okay, we took the same pattern, the same sample, 10,000 times, and then we can look at the mean, how the mean change in time, and how the variance change in time. We saw that the mean is changing because of our original signal, and the noise is still the same.
Because the mean changes.
The mean is changing, yes.
So stationary, right?
No, because all of the other statistical properties still still is the same. It doesn't matter where I took the sample. Of course, without the mean, everything else is the same. So we can treat the noise, the Gaussian noise, as stationary.
The noise is stationary, but
Yes.
signal
The signal is
to the
changing.
noise is
Yes,
not changing.
exactly.
Okay.
Yes, but here the noise is definitely stationary. And now, again, we looked at two processes, and we want to describe first by eye if there is any elephant in the data.
Looks like the fluctuations on the right are more dense.
Okay, definitely. Sometimes there is this burst of activity, right? And it seems that maybe the mean is the same or the variance is the same, but we can see that there is more density of these bursts, and maybe we can stop with one of them. Yes. So here we can see exactly what we saw a few seconds ago, and here we can definitely see that there is more fluctuations also. Okay. So we can guess that these are not the same processes, but we can start look at the properties of them. So let's look at one example, one on top of each other. Okay, so it's exactly as we did yesterday when we want to eyeball something. It can be a good experience to look at a lot of samples and then just to plot one on top of each other and look for differences. So here we can definitely see that it seems like the green has more fluctuation, but the mean seems like they're both going up the same way. Okay. Now, this is, it seems like exactly what we saw before that. This is the histogram of different points at in the second example that we ran. So again, it seems like the distribution of the first point is Gaussian, with almost the same shape as before, and it's stationary. Okay, so the noise seems like it's constant in time. So, and this is, again, as we saw just before that, this is the mean of the signal, and this is the variance of the signal. So it seems like it looks exactly as we saw just a second ago. Let me run the same code. Okay, so at least for the mean property and also for the variance of the noise in time, it seems that both of the processes has almost the same parameter, right? Although we did saw something that seems different in both of the processes. So let's try to describe something else that can catch the differences between them. So let's look at two-dimensional finite distribution and not only one. Okay, so these are the same correlations that we saw yesterday between 2 points. Okay. So it seems there is no correlation between two executive points. This is taken from the first sample, right? Now let's look at the second example. Okay, so now it's beginning to look like something. Okay, there is really high correlation. In our example here, it's negative correlation. Okay, you just asked yesterday if it's only if it's only positive correlation. So here we can see the diagonal is on -1. Okay, so just to plot it. again. So although the two processes by now looks the same, we see that there is highly correlated stuff that's going on in the second example. Okay, now let's look at more high order correlation. Okay. So this is exactly what we just saw. This is the second order correlation when we took two executive points from the first sample. So there is no correlation at all. And here we can see highly negative correlation. And I'm going to take it by steps, and each step to increase the time interval between the dots. Okay, so this was 2. Now it's 3 dots. We can see that this one still has totally no correlation, and this has some positive correlation. Okay, which is exactly the opposite of this. This is 4 points interval. This is 5 points interval. 6. Okay, and still I can go on and on in time until the point that it started to seem really uncorrelated. Okay, so by now I think the two processes seem totally random at these intervals. Okay, and it teaches us something about the correlation inside the signal and the fluctuation of the correlation. And what we did yesterday was to look at the cross correlation or the autocorrelation. Okay. So here we're going to look at the cross correlation of these two signals. Okay. So and what I'm plotting you now is the cross correlation coefficient matrix. So we're gonna think about it as we can choose a line here. Okay, so let's look at one line. One line will be, okay, it's not exactly as I wanted, but you can see that only the diagonal here is 1s. All the other values are 0. Okay, why is it 0? Because it is measuring the cross correlation with each sample with all the other samples. So if we're going to take one line, it's like autocorrelation of one signal. And we took the signal and cross-correlated with itself with 0 leg. So 0 leg is exactly what happened on the diagonal. So it's 1 because the correlation with the signal with itself. And if we'll take one pixel to the left, it's like we did one time shift. Okay, and we saw that for one time shift, there is no correlation between the dots, and in that process, we saw that there is none at no time shift. And in this process, we can see exactly what we just saw in the correlation plots, that on the diagonal, it will be 1, but around the diagonal, something interesting is happening. Okay, so the diagonal is exactly 1. I don't know if you can see, but that point. Now, if we're going to shift the trace one to the left or one to the right, it doesn't really matter. We're going to have a -1 correlation, really high negative correlation, exactly as we saw at the correlation plot. And for each step, the sign of the correlation is changing, so there is high rate of fluctuation in the correlation. But we can see that it's only happening for some distance from the diagonal, and from then it started to be 0. So 0 correlation, exactly as we just saw here.
What are the axes?
So the axes are all of the sample correlated with all the other samples. It doesn't really matter for us right now, but here we can nicely see the radius of the correlation. And again, we can see that there is some area with great fluctuation of up and down negative correlation, and from some place it is beginning to be 0, And I'll show you this example again. So this exactly demonstrates us what happened in 2 time shifts, 3 time shifts, and at some point after around 20 or 30 time shifts, we can see that both of the signals are 0 again. Okay, so we found one uh, one parameter that we can actually describe the differences between those 2 processes. Okay, I can now tell you that the way that I made the second process was to just filter the first process with some filter. Okay, maybe you can guess that the filter was that I took only, or I amplified the fast fluctuation, and that's the reason that we saw a lot of fast modulation on the signal. Okay, so filter is somehow like amplifying a certain frequency, and we're going to talk about it in the SFT part. But just now I wanted to show you, or to give you some feeling about the parameters, the different parameters of these random processes, and some differences between them. And at the end, only when we look at 2-dimensional finite description of these properties, we saw the change. Okay, I think we can take a little break right now. Let's say 10 minutes. Okay, any questions? Great.
כן, רב שפת זה דיפלום. זה דיפלומה. רגע, למה חינכתם? כאילו, הייתי כנראה מופתע, כאילו.
שכאילו צריך להראות שכאילו השיטות חדשות של קודינג, כאילו הקודינג מאחור הזה, כאילו גם קודינג בעצם כאילו לא כאילו אם שומרים על זה שהזמן יכול להיות שמצלצלים
לא, אבל עגבניה
אתה לא רואה
צריך לבוא עם עגבניה שלמה.
אבל הם אומרים שכאילו אם אני מסתכל על
לא, אבל תראי איך העגבניה
אבל זה דווקא הגיוני
ואם היית אוכל את זה בצורה, אם בכלל זה אם היית שם גם מלח, שמת מלח על העגבניה הזאת, בכלל זה איך היה שואל את כל המים החוצה? לא טיפי. אתה יודע מה זה אסנס חדשים? זה קראת מאיר שלו זה נראה לי בביתו במדבר יש לו אסנס חדשים
סימטריות, או שיש
אז מקסימום
חלק,
אני אוסיף
יש לפעמים קורלציות בין
כפוף
כמה
יותר
דגימות,
ועובר
לצורך העניין. אנחנו עוד שאני מסתכל על תהליכים, כאילו יש לי כמה דוגמאות קטנות שאני לא אכנס לכולם.
כן, יש
התהליכים שהם
מידע
כאילו
אישי,
גאוסיאנים, או תהליכים גאוסיאנים שיש להם סטטיסטיקות בסדר גודל יותר גדול. שיש להם קצת קורלציות, סך הכל ההגדרה של גאוסיאני שההסתברות בכל נקודה היא לקבל הסתברות גאוסיאנית. זה יכול לקרות כאילו בהרבה תהליכים, למרות שכן יש בהם איזשהו קורלציה ביניהם.
יש לי שאלה על המטריקס קורליישן שהראית?
כן.
יש לנו בעצם נכון את המטריקס, בדיאגונל זה 1, קורלציה של 1 תמיד.
זה סיגנל עם עצמו.
סיגנל עם עצמו. עכשיו, זה סימטרי לזה, נכון? בעצם אין לך שום מידע פה, נכון? עכשיו, בעצם כל נקודה פה, כל ארי שיש לך פה, הוא קורלציה עם משהו שיש בחוץ, נכון? בין זה לזה. ואז באמת יש קורלציה כזאת.
כן. כאן
אבל
כאילו,
זה לא
שאתה אומר,
פשוט מבין, כאילו זה I, נכון? וזה נניח J.
כן, אז כאן כאילו ב-I1 ו-J2, ונסתכל על הנקודה כאן, זה שלקחתי את הסיגנל הראשון, אז ב-1 עשיתי קורלציה בינו לבין עצמו.
ב-1-1, זה.
כן, זה J שווה 1. הלכתי ל-I שווה 1, J שווה 2, אז עשיתי טיים שיפט 1. אז זה אני מחזור.
או טיים שיפט, אוקיי.
כאילו, אחד ישב במקום ושני ידע.
אבל יכל להיות מצב אם אתה עושה את ה-correlation matrix, שבו יש לך איזשהו אין סיגנלים, נכון? סך הכל. ואז אתה עושה בעצם correlation matrix עם כמה אין סיגנלים. ואז זה בעצם אוטו-קורלציה, שזה חייב להיות 1, וכל השאר זה בעצם הקרוס-קורלציה. נכון? אוקיי. אבל במצב הזה פשוט אתה הזזת. זה אותו סיגנל, אלא אם הזזת.
כאילו אנחנו נסתכל על זה עוד מעט, אבל כאילו, אם נסתכל על החץ הזה, בהנחה שזה היה אותו סיגנל עם עצמו כל הזמן. כאן אנחנו נקבל את האוטו-קורלציה שראינו אתמול. אתמול היה לנו סיגנל שנראה כזה דבר. מבין מה אני מתאר בערך? כאילו זה היה נראה ככה. אז כאן היה לנו 1 וכאן היה לנו שני 1.
אבל זה, הפיק זה חייב להיות פה.
כן, כן, זה היה...
אתה יכול ללך עמי. כן?
אתמול נראה לי שהיה בסדר גם. היום יהיה קצת יותר קשה.
כן. אתמול לא הספקתי לקבל משהו ממש מהחבר'ה, אמרו לי שהחצי השני נכנסת יותר לדברים תיאורטיים.
כל זמן...
אתה משחק על
אני בטוח הלכתי הרבה פחות תיאוריה ממה שזה היה. אבל לא היה הרבה דברים פרוסים. כאילו אחר כך דיברתי עם אנריקה, אני שואל אותך על זה. היא אמרה שלדעת את זה, יותר זורם ופחות הארדקור תיאוריה
ממה שהיה שנה שעברה.
ממה שהיה הצד.
כן.
אתמול נראה לי הרוב היה די ברור לאף הדעה בגדול כאילו מעדיף שזה יזרום שהם ישאלו.
ואתה בינתיים רץ לפי הקצב שאתה...
פחות או יותר. אתמול זה היה בול. היום זה ישתנה כי פשוט יש הרבה יותר חומר וגם יותר קשה. אין מה לעשות. אני אנסה כן לסיים את זה שעה פחות ממה שתכננתי כדי שאני אכניס גם עוד משהו שהוא לא קשה. כאילו לפחות מחר אני לא יכול.
ויש להם איזושהי אפשרות היום להקל בדברים?
כן.
אתה תעלה את
התרגיל ממש. תרגיל ממש. תרגיל ממש אני חושב שתלוי לאן נגיע היום החומר. והעליתי להם את הקוד של כל הדברים שהם. כאן נורא קשה לראות את זה.
אז הצבתי על הקוד, יש שם המון דברים שהם רפרנס לקוד אחרות.
לא המון, יש שם כמה מקומות קטנים שהם משתמשים בדאטה.
לא, אבל יש שם נגיד לעלות את אלי
נכון,
מפה
נכון. אז
ולעלות
זה
אלי
דאטה.
אילת וכאלה.
רגע.
אוקיי, זה דאטה.
הדאטה, כאילו אני יכול להכווין אותם בדיוק לקטעי קוד שהם לא צריכים דאטה.
אוקיי.
אז מתם יעבדו על דאטה שאנחנו מסנתזים בעצמנו, וכאן אפשר, חצי שנה אפשר לעבוד על כדורים כאלה, כן? שניתן להם לתרגל קצת מהתהליכים שעכשיו ראינו, שזה תהליכים רנדומיים, וקצת על FST. כמה שנגיע לזה, אז אני אתן להם לקחת את הקטעי קוד האלה ולהריץ אותם בעצמם. אז זה לדעתי לגמרי סוגר להם את הפינה, נורא פשוט, הם לא צריכים דאטה מבחוץ, לא צריכים לשבור את הראש על מה זה הדאטה ואיך הוא נראה, פשוט לסנטז לעצמם תהליכים פשוטים, סינוסים, תהליכים רנדומיים, לשחק עם זה קצת, לראות את המאפיינים.
לא יודעת.
זה סינוסים. בכלל עם קוסינוסים.
זה לא יפה שאתם מדברים עליי שאני לא נמצאת.
אז זה לדעתי, אפילו פשוט תלוי כמה נצליח לעשות היום עם FST.
ובכל אופן זה לא נחשב.
מיטי אמרה לי שהיה משהו.
כן, דיברתי איתה, היא גם אמרה לי שהיא מאוד נהנתה ושהיה... אמרתי לה שהיום יהיה יותר קשה.
היום נחמד. מה? כן.
חוות עם נשק בחוץ, זה לא יהיה יותר קשה.
כי אתם למטה, כל החיידקים יורדים
למעלה,
למטה.
כל החיידקים עולים למעלה.
זה העברור שמה היה כל הזמן? מאוד טוב.
טוב, בסדר, sounds good. אז תיתן להם את ההזדמנות לתרגם עם
כן, כן, היום בסוף היום אני אראה בדיוק לאן להגיע ואני אתן להם לעבור על בסיסים של שורות קוד. כאילו נראה לי הכי טוב.
לכמה שנים אתה עוד פה?
יש לך,
תלוי את מי שואלים, אבל יש לי עוד כמה שנים.
עוד כמה?
יש לי עוד כמה שנים.
חשבתי שאמרת 5.
התחלתי רשמית התחלתי את הדוקטורט לפני שנה. אם שואלים את עדי, אז כאילו הדברים קצת שונים.
למה לא?
כי כאילו עשיתי ישיר דוקטורט, אז הייתי אצלו שנתיים במאסטר. אז אני חושב שאני הייתי מאמר על 3-4 עם נגד.
זה בדיוק כשזורקים אותנו.
ואם אנחנו מצליחים להמשיך את זה, מבחינתך זה...
זה אחלה.
הוא בנה את זה.
working on it.
לא, לא,
ראית את המייל הזה מיונתן?
לא, ואז זה גם הכי כיף לי, כן? כי עכשיו אני כאילו... אני עוד אעשה טעויות, כן? אני עוד אעשה דברים שכאילו, אוקיי, כאן הם יקצצו אותי בכל מיני דברים, ואז אני יכול לשפר את זה. ולא רק לחזור ולהגיד, אוי, לא ידעתי את זה. טוב?
נראה שאתה נהנה.
אני ממש נהנה. בוא נקרא לכל חברה.
מה, היום יש?
אל תרים ידיים. היי, היי. Okay, ready? Let's go on. So I'm going to try to run it, about it a little bit faster because I know some of it seem a little bit boring or trivial or not trivial, but we want to get to the more fun parts. Okay, so we discussed and we saw some joint Gaussian variables. I think that we did it, right? Yes. So we stopped here.
Okay, so we saw that the distribution Gaussian, the distribution of each sample by itself is Gaussian, the joint distribution of each pair of samples is also Gaussian, and the joint distribution of each triple of sample is Gaussian, and so on and so forth. And we saw also a process which had some correlation between them, but the distribution was still Gaussian. Okay. So to be pedantic for your own, and let's see some more examples. Okay. So now I'm going to I just made these two vectors which are random, and we're going to look at some distribution of them. We're going to look at the first distribution, second order distribution, and third order distribution, and we're going to try to make some correlation and get some intuitive about the correlation between them. Get some intuition, sorry. So this is two totally random vectors and the correlation between them. Now I'm going to make a new vector, which is the sum of these two. Okay. And this is the correlation between the original vector and the new vector. So we can see that we added some correlation, right? It still builds from the same original two random vectors, but we additionally add the correlation. Okay, this is the same thing. And now I'm going to plot some variation of the same addition, but with different slope. Exactly. Thank you. So now I'm gonna. This is the correlation of the original vector plus the vector we just created, correlated with the second vector. Let's see if we can see some correlation between them. So we will just hold it and plot the correlation that we just saw. Okay, so the green one is the first vector with the new vector that we did, and we see that the slope is high. When we correlated the red signal, so the red signal was the first signal with the new one against the second one. We still see a correlation, but it seems like the slope is much lower. Now it's different manipulation. So we're going to take half of the amplitude of the second vector with third of the first vector. Okay, so instead of just adding 1 to 1, we're taking different ratios of them. Okay, and we got some nice correlation. Okay, so we can see some differences in the. Oh, sorry. So there are a few differences in the shape, in the slope, and also in the spreading of them. So we understood that the slope tells us something about the correlation between points, but the shape or the dispersion tell us about the precision of this correlation. Okay. And we can continue. Okay, so this is totally random. When I took the second vector and I took off of it the first vector, so now it's totally uncorrelated. Although R3 was the addition of two vectors. So when I'm doing subtraction, I get no correlation at all. And less correlation, it's exactly the same vector with itself. So it's the way that I built the correlation. It's the first vector with the second vector correlated with the third, and we can see that it fails exactly on 1 to 1 because it's obvious. Now let's try to look at the third order distribution when we're going to correlate everything with everything. Sorry. Hold off. Okay. And I think this is nicer. We can see three axes here. So the first axis will be the first vector, the second vector, and the third vector. And now, from this point of view, it seems like it totally uncorrelated. But the nice thing with plot 3, which plots the data on three-dimensional axis, that we can rotate it. So from that point of view, the data seems totally random with Gaussian distribution. And if we rotate it, we can find the nice correlation that we saw earlier. Okay? And we can actually rotate it in two-dimensional to see the correlation exists in many different planes. Okay, so although the data could seem Gaussian and random, there is some dimensionality that we can still see correlation. Okay, and this is obvious because this is the way that we built our data. Okay. Now, let's see another example that still the first dimension is Gaussian, but it's not going to be jointly Gaussian. So I'm still handling the two vectors that I just created, which I remind you they're random. So this is the histogram of the one of the points, and this is the histogram of the second point. But now we're going to look at the joint distribution, okay, and something different happened here. Although these two processes are still Gaussian. So here by force, I chose not to take all these points and all of these points, but still other properties are the same. Okay, so this was one example. So a one-dimensional Gaussian variable is fully characterized by its mean and the variance, and this determines its probability density function and therefore all other quantifiers, just as you mentioned, right? It's very easy to characterize first dimension Gaussian process. An nth order of Gaussian variability is fully characterized by the mean of each component and the covariances between the components. So this covariance matrix holds the information about the variances of each of the jointly points distribution, the jointly distribution of different points, and also the relationship between them. And this determines the joint probability density and therefore all other quantifiers. So if we have a Gaussian process and we know all the means of everything and we know the covariance matrix, we can almost fully describe the whole process. Yeah, so in particular for Gaussian variables, lack of correlation is equivalent to independence. It's not necessarily true for other types of variables. Okay. A random process is Gaussian if all finite dimensional distributions are jointly Gaussian. A Gaussian process is determined by specifying the mean in each moment in time and metrics of covariances between the values of different moments in time. So we just said it. And all finite dimensional distributions are Gaussian and are therefore determined by the above data. Okay, stationary Gaussian process, as you might conclude yourself. So if the process is stationary, so the mean and the variances are constant in function of time, and also the second order distribution do not depend on the absolute time, the joint distribution between dots, and all of these things we already saw yesterday and some today. Okay. This you can read later. Again, you can read about the autocovariance function and then different names and the different meanings of them. And there are many processes with same means and covariance function, but only one of them is Gaussian. And there is an example in the MATLAB. Again, you have the code, and you can run it yourself and see other examples of random processes which are not Gaussian, although they might look at Gaussian. Okay. Now as I said at the beginning of the first lecture, today we want to find a relationship between some parameters that we can look by eye, or we can feel more comfortable with the intuition about them, which is the rate of fluctuation and the autocorrelation function. And from here we want to get to the FFT, or to the Fourier transform. So the autocorrelation function reflects the rate of fluctuation that's presented in the signal. Okay, a slow signal will have a slowly decaying autocorrelation function, and the fast signal will have highly oscillating autocorrelation function. So let's see it. Okay, so you have a lot of remarks in the MATLAB code. Here there is an example for a different stationary process. You can run it later. This is stationary and Gaussian. This is another example for a random process, stationary and Gaussian with different properties, which is actually nice, but you can look at it after this. And let's look at the autocorrelation functions and the fluctuation rate. Okay. So these are the three examples that we started today. So let's look only on the blue line. So the blue line is, it seems like the mean is around 0. It has some variance, and we can look at the autocorrelation function. So the autocorrelation is the blue line here. Okay? And we see a large correlation only when the signal is with itself, and when we time shifted it, we see that all of the different time shift correlation are around 0, more or less. Now the second signal is the green one. The green one is the signal that we high-pass filtered it. So we kept a lot of the high frequencies, but we throw low frequencies. And what we already saw many times today is the autocorrelation, the signal with itself, in different time shifts. And we can see that the rate of correlation is fluctuation really fast. Okay, so one correlation in one time shift is high positive correlated, and in the next time point it will be negative correlated, and it changes very fast, but after a while it decays and becomes 0 at all of the other points. And the red signal here, which had the lowest or the smallest width, and we can see that almost there is no high fluctuation inside it. So this is the opposite of the green one, which is the original signal filtered with the low frequencies. So we can see only low fluctuation, and here in the signal we can see that the rate of fluctuation in the correlation is really low. So here we have energy, and it's decaying until it became 0 also. Okay, and you can imagine, or I will be happy to think that after what we did yesterday and today, you can also imagine why this phenomenon is happening, right? Because when we look at the original red signal, when we going to time shift it, so each point is not very different than the point behind it, right? That's the meaning of the correlation here. So we have also some feeling about the rate of fluctuation in the correlation. I know it's very hard to say it a lot of times. Yes?
What is the difference between autocorrelation and cross-correlation?
So autocorrelation, usually the name suggests that you're gonna correlate with the same signal. It's autocorrelated, and you can time shift it. Cross-correlation, usually it's when you're doing it with two signals, and you can do a correlation between signals, which is one correlation, and you can do a cross-correlation, which will time shift both of the signals.
Cross-correlation could be also between two different signals, not just time.
Yeah, exactly. That's exactly what I meant. Cross-correlation can be two different signals or more. Yes. Okay. Go to PPT. Okay, so right now we talked about rates of fluctuation of stationary processes, and let's start to talk a little bit about the spectra of the stationary processes. So I remind you again, the philosophy that we're talking about, and we talked about it yesterday and today, we always want to separate signal from noise. For that, I remind you again, we need to actually describe what is the signal and what is the noise. It depends on the experiment, etc., etc. But here we want to use rates of fluctuation for that purpose. So we saw that rates of fluctuation are related to the correlation structure of a process. But the time domain description of random processes, okay, even the stationary ones that we just talked about them, they can be actually really complex, as you saw. There is a lot of different correlation in time, and even if we know the mean and the distribution and the PSD, if we know how to describe the properties of the distribution function in time, it will be very hard to describe the whole process. Okay, so we want actually somehow to describe a sample with a more easier way. Okay, so as I said, there is a lot of correlation which makes life difficult to describe these kind of processes, and we want a less correlated description of stationary process and even more simplistic. And the way that we're doing it is with frequency representation. Okay, so we'll begin of little theory about it, and then we're going to play with MATLAB a lot. So generally, every signal can be expressed as a sum of sinus waves. Okay, who of you heard it in the past? Okay, great. So actually here is written with sum of sine waves. Of course, it can be also with cosine waves. Yes. So let's see what does it mean when we're saying this. So these are sinus waves. Okay. The green line is a sinus from 1 going to -1, going to 1. We have the phase of the sinus. So at 0 it's 1. At pi phase it's 0, and again, and the blue line starts with the same dot, so it's still a sine wave, but with different frequency. So for our condition, or usually for standard conditions, which is finite duration sample signals, it is enough to use the sample sine waves with frequencies of 0, 1 on the duration, 2 on the duration, and so on and so forth, until we get to the frequency of 1. So these frequencies are called Fourier frequencies, which is not necessarily a standard term. So sine waves could be also different in amplitudes, and of course we need different amplitudes to describe how every signal is built. And it could be the same amplitude and the same frequency, but at different phases. Now we need all of these different properties in order to build any type of signal. So by varying the different amplitudes and the different phases, we can generate all possible signals. Okay, and let's start to get some notion with these types of things. Okay, so here above, I have a sinus 1. This is the equation. And we can see that it starts in a certain point, which is not 1 or 0, and it's going on into time. Now, in that box, anybody can guess? It has 0, 1 in entry 1, and all other zeros. So actually, this is representative for the amplitude and the frequency of this signal. So this signal has it inside of it only one sinus So all the other frequencies are 0, 1 sinus with 1 hertz in amplitude 1, and this will represent for us the phase of the sinus. Okay, so because it doesn't start at 0 or 1, it has some phase on it. So now we want to see what will happen. Okay, so the green was the original signal that we just saw, and now we have I've added a new signal, which is the red one. Okay, so here is the formula for the red one. The blue one is when we add the two signals together. Now if we're going to look at the frequency descriptors of these signals, we will see that it has a new entry. The new entry is on frequency 3, and it has some amplitude. We can see the amplitude of the red signal is indeed lower than the green one. In that panel, we can see that in frequency number 3, it started in a different phase. Okay, and we can see that it started in a different phase. And when we added these both signals, we get the blue line. Now, this is example of how to read the frequency panel and also phase panel. And we can continue with this process and add more and more sinus waves. So here I added the 5th element. So there is the frequency number 5 with low amplitude and in different phase. And again and again. And if we'll continue with the same formula, we can see that from this only finite amount of sinuses, we can see that the shape that we're going into to build here seems like a square wave. Yes?
Where do we see the phase shift in the formula?
We won't see, we can't see the phase. It's not exactly the formula. You're right. Okay. Just it's almost the formula of how to do it. Okay. But we will see it in the code. Okay, in the MATLAB code we'll have everything. So this is a simple example of how to build almost any type of signal from stuff that looks like a sinus wave. Okay, and it's somehow surprising if you're not familiar with the idea of it. Okay, so this is one wave that we can build. Another wave that we usually want to build, or we have a lot, we can see it a lot in the data or when we use filters, is the impulse. Okay, impulse means that we have quiet all the time, and at some sort of time we have one. We have 1 point with one data inside of it. So it can be click or impulse, and surprisingly, also this could be built only with sine waves. Okay, and the way to do it is to add actually all the different sine waves and to set the phase of them to be exactly at the same point. Okay, so when we go 1 point to the left, all the different sine waves here and also here will eliminate themselves. So when we take a lot of different sine waves, it's going to be 0 at all the different times and 1 here. Okay, some more intuitive on it. So if these are the signals, we have a function to transform them into the frequency domain. Okay, so this is the time domain, this is the amplitude domain. Our function will take the signal and break it into the frequency and amplitude domain, and what we cannot see here is the phase domain. And the nice thing that I already want to present here, and we will return to it, that this transform from the time domain to frequency domain, of course that we can go the other way around. So we can take the frequency domain with the phase domain, and we can do the reverse transform to get the time domain again. So what I'm basically saying is that all of the information is kept on the two sides of the function. Now some basic properties. We can see that here there is one sinus, and the amplitude spectra of it will be, I don't have the media. Never mind. So this sounds like and we have one frequency and one amplitude, and we can see that because it is a narrow band signal. Okay, it has only one frequency, but as we see, the signal in the time domain, it must be long. Okay, so we'll see in a second why it has to be long. Okay, if we'll take this signal, which I can't do with my own voice, okay, try to imagine how it would look like. There is a beginning of a sine wave, and it decays very fast. And if we look at the spectral domain, we will see that it has a more broader area of frequencies. But and the click in the opposite around, it sounds like click. This is click. It's very fast, and in the frequency domain, it has all the different frequencies. Okay, but so here it's the totally opposite case. Okay, it's very fast in time, but it's really broad in frequencies, and actually this is the reason why a tone must have a long duration. Okay, a tone with only one repetition will sound like a click, right? So I'm just trying to give you some intuitive about it. Tones must be at some longer duration in order to them to be tones.
There is a criteria for how long?
It has to be at least 1 period.
So 1 period, it depends on what is the question. Okay, to do an FFT, there is some criteria. To be able to discriminate or to recognize tone, we need at least 5 or more, around 5 repetition of the tone. Okay, so this is just an intuitive. Just want to mention the converse is not true. It is possible to make long duration broadband signals, okay, with broadband frequency channels. So this is exactly noise. Okay, it's like white noise. It's like it has a lot of different frequencies in a lot of different lot of bands, and it's long in time. Okay, so the practice of Fourier transform is not as easy as the theory. There is a lot of technicalities, and especially when we're using MATLAB. So MATLAB has its own Fourier transform function, and it's not as simple as we want it to be, but don't worry, we'll see how we can tackle it. So some technicalities about Fourier transform. We are allowed to vary amplitude and phases of the frequency component, and usually we are describing the Fourier transform results with a complex number in order to designate the weight. What does it mean? That the length of a complex number represents the amplitude of the sine wave, and the angle of the complex number represents the phase. So instead of talking about two different numbers at each step of time, we can just represent everything as a complex number, and MATLAB actually using a complex number when we're using FFT. Okay, so sometimes it's convenient to write this number as a complex number representation of the R, which R is the length and theta is the angle. But this type of representation can be also x plus iy, which I is the complex number, and x is r cosinus theta, and y is r sinus theta. And sometimes it's very comfortable to write everything like this, because then we can do a nice computation with MATLAB. So the x and y are called the Cartesian coordinates of the complex number. I guess you knew that. So as I said, each representation is best for other needs, depends on the context. And some example of when to use what. For actual manipulation and for some theoretical issues, the Cartesian representation is better. Okay, so let's look at how FFT looks at nice signals. So we're gonna generate a signal, which this is the way that we're gonna do it. So we're gonna use cosine, and the cosine is the MATLAB cosine function. Pi is the constant pi. The argument to MATLAB trigonometric function are always in radians. So, as we saw earlier, the parameter here should be from 0 to pi, from 0 to 2 pi, which is one cycle. And we are going to generate 1024 points here for every cycle. So we need to multiply it here, okay, in order to actually get at the first point, we will get a cosine of 0, and when we get to 100, close to 1024, we will finish a cycle. So let's look at it. So can you see any of the code? No, huh? It's totally scrambled. So I'll read it. So this is exactly what was written on the PowerPoint. I have a signal, which is cosine of 2 pi 1024, and I plotted it. Now I'm going to, the next function will be fsig equals FFT. FFT is the FFT function of MATLAB. It's a built-in function. Can I do what? Sorry. Enlarge the font. Let's try to.
I just did it. Home. Go to home.
Yeah.
References somewhere.
Yeah, I know how to enlarge the font.
I just did it yesterday, so I know.
Thank you. Is this better? Okay. So this is the formula that we just saw, and I plotted the signal. Now I'm going to plot the result of the FFT. Okay, and it looks like this. Why? Do anybody has the answer for what do we see here? It's totally different than what we expected, right? Okay, so the answer is really simple. The FFT return fsig. We can look at what is fsig. So the data is complex numbers. You cannot read it, but this is 1024 points of complex numbers, and this is exactly what I just said to you, that FFT uses complex number. If you want to look at it as the amplitude domain and the phase domain, we need to look at the real part of this complex number and the imaginary part. So the blue line right now is the amplitude domain, and the green is the phase domain. And let's zoom in a little bit. So first of all, we can see that the x-axis, both of them, are 1024 points, which is exactly the length of our signal. So this is important. And now we will zoom in to see what exactly we have here. So we can see that everything is 0, the green and the blue, except for one point. Okay, and that point is at entry number 2 with amplitude of 512, which is exactly half of the number of the samples that we ran through the FFT. Now we can see another thing. It seems symmetrical. We have also the same frequency here. Okay. So at the almost last point, okay, here is the last point. We have the same thing. It's the amplitude is almost the same, and this tells us a hint that we will always see a symmetrical picture here. Okay, I'm not going to discuss why exactly right now, but somehow you should know. Are you familiar with the name Nyquist or Nyquist rule? Okay, so the rule is that if we sample any sample in the real world, in order to describe it, we must sample at least twice faster than the fastest signal inside it. Okay, and what do I mean? So it's just a few words about it. Let's imagine that I have a sine wave in the real world, and now I want to sample it and to build it again from my samples. Okay, so if I will sample, let's say that I will sample only one point. Okay, so if I have this point from all of this trace, it will be extremely hard to build the function again, right? So let's say that I have few points in some sampling rate. Okay? So if I have sampling rate of the same sinus, okay, so let's say that I'm sampling here, and I'm sampling again each time that the sinus is at the same point finished a cycle, here, and again. So from those 3 dots, I get still some sort of line that I can't rebuild the original line. So in order for me to sample a signal and to be able to build it again later on, I must sample it at least twice as fast than the slowest sinus wave inside the sample. So here I need to sample it at least twice as faster than the original.
And this is 4 times faster.
This is 4 times, but this is just an example. Okay. So here actually this won't give me anything, but if I have a lot of many different time points or shift it, and then I have this signal, and then I have this signal, so at the end I will be able to reconstruct it. Okay. But as a rule of thumb, we need only half of the frequencies in order to build the fastest frequencies that there is. And this sometimes it can gives us a nice intuition about why the Fourier transform is actually symmetrical, because all we need is only the half part of all these frequencies in order to describe what's inside the signal. It's not that important for now, but it's something that I need. It's a must to understand in order to talk about this thing. Okay, so this is the basic representation. Okay, and an important thing to mention is that we are talking only about the discrete Fourier transform. Okay, the non-discrete Fourier transform is different than what we are dealing with. So we already saw that the discrete Fourier transform in MATLAB is complex, even when the imaginary part are 0. If the imaginary part is 0, of course, in our case it was 0, meaning that the phases are 0, and it has a symmetry. Now we added some value. We added something that is constant to all of the signal. So the DFT will look almost the same, but we change one of the frequencies. So what we saw here that only the second entry has some energy in it, although we looked at a signal which looked like this. Okay, only one cycle. So it represents the second entry of the FFT is +1 the number of frequencies that we had originally in the signal, okay, and that was for us, okay, that is true because sometimes we want to describe other functions. So this function is exactly the same, but we added +1, so the mean now is different. So we can think about it as a combination of the same frequency with another frequency which is 0, which is like a DC current, which is 1 at all the different times. Okay, and this is the way that MATLAB represents a DC shift. So in the MATLAB, we can look at the Fourier transform of this signal. And now we will see that there is entry in 2 and entry also in 1. Okay, so these are really tricky because a lot of times people are doing Fourier transform in MATLAB, and sometimes they forget that the frequency is not the x-axis, it's x-axis +1. So the first one was the DC, and all of the others are the frequencies. Okay. Yes, so an easier notion to 2 times pi divided by the number of points that we call the second. So instead of calling it this way, we're going to call it eventually hertz. Okay, so formally this is called the angular frequency and is marked by omega. But this is also the frequency for generating 1 cycle, so we call it 1 hertz. Okay. The vector of sampling points also appears at all times, so we call it something. Usually we're calling it time because it's time. It represents time. So let's see more stuff, other simple stuff. So the signal, we're going to look at signal that is built from 2 cycles, 10 cycles, and 1 cycle. And the notion here is that t represents 1 second, and we need to remember that in our case, 1 second will be 1024 samples for a second. Hertz will be 1 cycle for a second, and the number here will represent the number of cycles that we have in 1 second. Okay, so we just called a parameter called hertz, which is 2 times pi divided by the number of samples. That's what I just said. We have time, and we have our signal. And let's look at it. Okay, so we can see that it starts at 1. It has 2 nice cycles. One important thing is that we can see that the signal actually ends when it started. Okay, so our examples here are extremely nice and simple, and that's the reason also that the Fourier transform seems also nice, extremely nice. It's extremely simple. We have it at entry 3, all the amplitude inside of it, and all the phases are 0. Okay, this is for sinus 10. Okay, and again we can see the same thing here. So the entry will be 11, and on 300 the same thing. Okay, so now there is a nice thing here. Remember that we're sampling at 1024 points, and I want to represent a cosine wave that is doing 300 cycles per second. So when we're going to zoom inside this signal, it doesn't look like a cosine, right? So the points that we have are the dots inside. This is exactly our sample, and the lines here are the lines that MATLAB added between each point, and it doesn't seem at all like something that looks like a cosine, right? It's totally different, but still when we convert it with the FFT, we still see that only this frequency got the largest amount of amplitude, and all the others got 0, and everything is 0 phased. So it's interesting to see. Okay, maybe we continue a little bit. Sorry. Go to MATLAB, go to PPT. Okay, what happened in the phases when we're not taking a whole, we shifted a little bit here. Okay, so this is the wave. We can see it starts from 0.5, and we can nicely see in the phase domain. So in amplitude is the same, and the phase domain at the same entry got some amplitude inside it. Okay. Here it's asymmetrical for other reasons. So, sorry. So here I just ask MATLAB. I'll do it again. What is f sig at entry number 3? So it's this, because it's a complex number. Okay, this is the Cartesian representation of it. We can look at the absolute value at this entry, okay, which gives us exactly half of the amount of energy. And we can ask what is the angle. So the angle is the function that MATLAB uses to get us the imaginary part of this complex number. And the angle is exactly 1, exactly as we build this signal, okay? Because it was cosine 2 hertz t plus 1, and 1 was the angle here. Okay, it's the radian angle. Okay. So we already mentioned the DFT is really complex, and now we can actually see it. The absolute value is still half of the energy. Okay. Before that, when we looked at only the real value, it wasn't 512. Only when we look at the absolute, which contains the length of the vector and also the phase, and the angle is 1. So temporary conclusions: the function FFT tells us the frequency, the amplitude, and the phases of sine waves that build the original signal. The frequency is given by the index that is different from 0. The amplitude is the absolute value at this frequency up to some parameter. In our case, it was the number of sampled points divided by 2. The phase is the angle at this frequency, and yeah, this is true only for Fourier frequencies. Okay, let's look at signal that it's not full Fourier frequencies. Till now, we only talked about frequencies that are multiplying or division of whole cycles in our sample. And now we're going to look at signal which is not whole. Okay, so the blue line is our signal. Okay, it starts around 0. Okay, it starts here at 0.55, and you can see that it's not full. It ends around beneath the amount that he should have been. Let's look at the code. Okay, it's 12 and a half cycles and a time shifted. Now let's look at the Fourier transform, and we can see. Let's look at the blue line. Something totally different happening here. So it seems like there is some positive values of some frequencies and some negative. And this, let's zoom in inside of these guys. So we have 12 and a half cycles, and we got 2 points of 13 and 14, which very high amplitude, positive or negative. And we can see also a lot of stuff that's happening in the phase shift, and some other amplitude here as well. So let's take a break, and you can try to think what happened here, and we'll answer this right after the break. So there are some points that I'm not talking them at all because they're not part of the material. But Ami asked me to give you some, the big Ami, not Ami me, to give you some small exercises just to play with it a little bit. And I suggested that you have the MATLAB code of everything here, and you don't need any outside data, so you can generate whatever you want and look at some data. And I think that a nice point will be to do an FFT, but this time generate different types of samples in different sampling points, sampling rates. Sorry, I used only 1024, and try to see what will happen if you take a longer or smaller, or what's the connection between the sampling rate and the Fourier transform. And one thing that I want to mention, there is a strong connection between the resolution that we can get. Okay, so at some point there is a big trade-off between the amount of points that we're looking at and the results that we got from the FFT. Okay, and I think it's a nice game to take a signal and to sample the signal fast or slow and do an FFT on different windows and see what the result will be. And maybe we'll discuss a little bit tomorrow about it. Okay, but the relationship is not part of the material in the course, and it could be very insightful. Okay, so we stopped at the Fourier decomposition of not a whole cycle of 12 and a half, and we saw that the representation is some kind weird. So here I plotted the real part and the imaginary part. Okay, it's this. But let's plot the absolute Fourier transform. So the absolute takes also the amplitude and also the phase. And here we can see, seems like there is energy at both of these frequencies, 13 and 14, which is -1, so we'll get 12 and 30 Hertz. Okay, so remember, in the original signals we have 12 and a half cycles, and here it seems like the energy is half of, not half, some of the energy is on 12 Hertz and some is on the 13 Hertz. And let's try to see what happens there. So intuitively, I would have said that because it's not a whole number, the Fourier transform here, it seems broken. Okay, what do I mean broken? It's like we don't have a good enough resolution to get this entry with 12 and a half. And maybe if we'll try to fit here some other function, let's say a parabola function, we'll get the entry of 12 and a half. So this is only the intuition, only my explanation. But let's look at what we can do with MATLAB in order to understand it. So usually when we're talking about energy, we're not looking at the absolute values, we're looking at 20 times log 10 of the amplitude. Okay, so those of you who learned some physics know this is the energy or the power. So it's a different representation of the same data. And here we can see the same thing, but in logarithmic scale. And sometimes we have a nice function which is called FFT shift. You can look at it later on, but what I just did here was to move the signal, to delay the signal, and we can see the continuous point at the center. Okay, so I just shift everything and put it in the middle. So now I want to see all of these three graphs together. And now I'm going to try to do to run some algorithm and to build this signal. Now, the way that I'm going to build this signal is by taking step by step the right frequency, okay, and to actually synthesize this frequency and to add one by one the other frequencies and see what will happen. So I think this is a nice piece of code that you can also run it by your hands today. And mainly the algorithm will choose point by point from the power spectrum and will synthesize each frequency by the sorting of these points. So let's see. Okay. So I took the maximum point, which was at the 13 entry, which represents frequency of 12 Hertz. And here, the green one, the green line, the blue line is always the original line. The green line is what I just synthesized. So I synthesized a sinus wave that starts at the right phase with the whole amount of 12 cycles. Okay? So we can see, I'll try to zoom in a little more because it's very hard to see. Okay, so sometimes there is nice correlation between the green and the blue, but we can see we still miss a lot. Okay, and in the last figure, figure number 3, I shifted both of the signals. Okay, so now it still looks like in some parts, oh, you cannot see anything, sorry. Okay. So here, these are the same signals, but I just shifted them. It's really hard. But you can see in the middle that there is a blue line, and it cut it off. So this is the point where they're not continuous. And here I'm trying to rebuild this signal. So the green line is again what I synthesized and moved in the middle, and we can see it clearly that in the middle it's not right. Now what I'm going to do is to take the second largest frequency. Okay, so I have a new square. So the second largest frequency is the 13 sinus, and I added it to the green that I just had. So now the green line is the summation of a sinus wave that is built from 12 Hertz and 13 Hertz. And we can see that now we have a better fit. At least at phases we have a better fit, but we still miss some of the amplitudes here and some of the amplitudes here. And when we're going to look at the discontinuity point, we're going to see again that the envelope starting to look good, and here it still doesn't look good. Now we can run the process a few more times. So you see I just added another 2 frequencies, and the way that I pick the frequencies is by the amount of energy that they had, and intuitively all the frequencies that has a lot of energy in the original signal can explain better the original signal. So again, this is the green line is the summation of 4 frequencies, and we can see that something is starting to be built here, and we can continue with it. 5, 6, 7, 8, 9, 10. Okay, so only with 10 frequencies, 10 different sinus waves, we got really nice result here, and a hint of what will happen here when we're gonna continue this process. But the way that we did this process was in a very gentle way of taking the right amplitude and the right phases of each of the frequencies and to combine them. Okay. Okay, so you got the algorithm here, The important stuff is when I took the FFT. Okay, so the FFT is here. I already did it, and I sorted all the amplitudes and the frequencies, and then I can zero all the other frequencies. Okay, so I know which frequency to take, and IFFT is the function that actually is doing the reverse, the reverse function of the FFT. Okay, so IFFT gets actually the signal that we just saw in the frequency domain and in the phase domain, and brings me back to the time domain. Okay. So we saw in the spectrum that there is many non-zero frequency. This is due to the fact that we're actually looking at a finite segment from a long signal, and that there is a discontinuity in the signal. Okay, the Fourier transform of sound wave that is a pulse, we already discussed about it a little bit. What will be the Fourier transform of the pulse? All the different frequencies, okay, with different amplitudes or the same amplitude. So the function is actually a delta of t, but there is some small thing that we need to be careful. Good. I know what it is. Sorry. Okay, just a second. Okay, so I created a click. The way that I created a click is to generate a signal which is zeros, and in one time point I put 1, and then I plotted it here. Okay, so everything is 0 except for this. In the FFT, I plotted the real values, again the imaginary values. So everything is 1, and all of the frequencies, all of the phases are 0. Okay, exactly as the theorem says. Now let's see what will happen if I do the same thing, but the delta function of the click will give us a click at the second entry in time. Okay, so this is the click, and you can believe me that it's in the second entry. And now something weird is happening in all of the amplitudes and all of the frequencies. Okay, so we're not getting the same thing. And why is it? Why is this? Okay, so intuitively, when we moved the spike, the click, 1 bit, now we actually want to delay all the different frequencies that we had in the beginning to have the click in another place, right? So this is the intuitive way to say, and if I will plot here not the real and the imaginary part and the absolute part, we will still get the same thing. Okay, but the phases are changed. So let's look at what happened. Okay. So actually this is, the blue line is the absolute part. Okay, so of course everything, all the energy of all the frequencies are 1. But we can see that something weird is happening in the angle. The angle is the green line. And there is also a nice function in MATLAB, which it's unwrapping what's happening here. So okay, so this is just, we connected the dots here. and we can see that there is some sort of angle to all of the frequencies. Okay, so this angle of all the different frequencies exactly is doing what we intuitively thought. It will delay our click. Okay. Now I did it the same thing, but with different frequency. It doesn't really important. Okay. Actually, the same example, but instead of giving the spike in time 2, this is a spike in time 4, and we can see how it affected our phases. So again, everything is 1, the phases is a little bit different, etc., etc. It's not very interesting. We can unwrap it, and the curve here, I'm always forgetting the same word. The slope can tell us something about the phases, all the different phases that we want to give to all the different frequencies in order to calculate where our spike is. Okay. So we talked about clicks not in time 0. And the phase is proportional to the frequency. Time shift of signal is expressed as linear phases component. Phase is related to temporal structure. Of course, we need all Fourier components to synchronize at peaks. Okay. So now we want to discuss the relationship between the amount of energy in frequency domain and time domain. And actually, I already said it, but there is a law, a Parseval's equality law, that says that if you count all the energy in the time domain, in all the times, it's supposed to be equal to all the energy of all the different frequencies. When you sum all the different frequencies, okay, components. So that's the word. So generally, when all the signals have 0 mean, the zeroth Fourier's component, and we can always just subtract the mean or do a DC shift, we will get it. Okay, so this is the constant here. The variance of the sample is the power. Okay, is the mean energy, not power energy. And the energy of each of the Fourier components is always less than the original signal, which this is actually quite trivial, as we saw at the example that I rebuilt everything. We can guess that each one of the Fourier transform component won't have the same energy as the whole signal, but if we're using all the components, we will get the same energy as the original signal. Okay, but and the nice thing that Fourier transform gives us actually a deterministic variability decomposition. And remember when we talked about decomposition of variables, we talked about noise and signals, variables, of how to decomposition them. So now we have a really nice and deterministic way to do it, and now we can maybe think about some noise or some signals that has a certain frequencies inside them, and we are able conceptually to look at the amount of energy for each component, and also to eliminate and synchronize and build it again. So this is philosophical way of actually, well, I'm talking too much. We're going to see it. Okay. Okay. So how's this connection to the random process? So here's the theoretical part. Okay. We have samples from random processes, and we want to transform each of them into the frequency domain. Now we can collect all the values of the frequency components at specific frequency, and these samples are actually a random variable whose distribution can be computed. So I'll give you your time to read all the correlation between spectral representation and random processes, but as I said many times, the frequency representation are much simpler than time representation, and they are much less correlated than what we saw in the beginning, in the correlation of the fast fluctuation rates in the correlation. And here we actually get different components of the frequency decomposition which are not correlated to each other. So it's much nicer in a way. Okay, now there's a part in MATLAB that I'm gonna skip. And also about the spectral representation. Maybe I'll say something about it. Yes, okay, so I want to say something about, so here's all the information about the correlation between spectral and time and frequency domain. And I'm not going to talk about them, but yes, I'm going to talk about additive models, as we already suggested it a little bit. But by now we saw how can we look at data and then to build it again from eliminating frequencies from the frequency domain. So in additive models, usually the signal is not stationary or Gaussian because there is a special shape in it, like spikes or action potential or evoked potential in NFP, etc., etc. And we will usually assume that the shape is exactly the same every time, or almost the same every time, and whatever is not the shape is going to be the noise. In our case, it's going to be Gaussian noise. And because we know a lot about random processes, and we know a lot about how to talk about them in the frequency domain, we can now actually do it. So the independence of frequency components in Gaussian processes is the frequency domain expression of their length of structure. So this is some kind of high-level, maybe complicated sentence, but what it captures inside it is that when we are looking at frequency decomposition of Gaussian noise, there is no correlation between the frequency decomposition component. Okay? So generally we will consider Gaussian contribution to our signal as a noise, sometimes in not true, not interesting. Getting rid of noise. If we know that our signal doesn't have much energy in a certain frequency range, we can filter out that range of frequencies without hurting much the signal. Okay? By this process, we reduce the energy of the noise more than we reduce the energy of the signal, improving signal-to-noise ratio. What we would like to do is to set all the frequencies that are not important to us, just to set them to 0. Okay? And we will see that this is not necessarily the best way of doing it, but it's actually a really nice example. Okay. So we are talking about additive models. I'm going to skip a lot of examples here. Okay. Now, all the codes that I showed you, you don't need the data that is written inside MATLAB. It's self-generated. So I have this picture, which contains data, generated data. So we can guess that the data seems like there is something there. Okay. So actually, I created it with the signal is a Hanning window, and I added noise on it. Okay. And I created many of these Hanning windows. Okay. Now we can look at the FFT of them. So actually, what I'm doing here, because there is a lot of random noise inside, I'm going to look at the histogram of the second entry of all of the FFTs. Okay? I'm going to explain it again, because we can see here there is something that looks like a sine wave, okay, or almost a sine wave, or let's not talk about full sine wave, but it seems like there is some sort of repetition of the shape of the signal. So when I'm going to look at the histogram of all the FFTs in the second entry of the FFTs, maybe we'll see something interesting, and we can see that the distribution seems like Gaussian. It means that in most of the samples, there is energy at something that seems like sinus of this frequency.
What is the second entry?
Of the FFT.
Yes.
Okay? The second entry of the FFT represents the amount of energy with this sinus of this frequency.
Are you checking only one frequency?
Yes. Okay, because I can eyeball it. Okay?
So what is the x-axis of the histogram?
The x-axis of the histogram is the number of samples that I've got with this amount of energy. It's like any histogram.
The y-axis is the number.
The x-axis represents the amount of energy, and the y-axis is the number of them.
Amount of energy?
Yes. Sorry. Thank you. But by eyeballing it, we can see that there is something that looks like 1 or maybe 2 hertz, or something that is very slow. Okay? And where we are looking at the histogram, we can see that definitely it seems like the case. Most of the samples have energy in the lowest part of the spectrum. Okay, and we can look also at the angle of them, at the histogram, and we can see that the histogram is very clear. So all of them has almost the same angle as we actually saw, right? It seems like most of the underlying sine waves beginning with the same phase, or almost the same phase, when we're talking about the slow frequency. Now, when we're talking about faster frequencies, so this is the distribution of all the higher frequencies, around 15, and we can see that the distribution it's not Gaussian. Okay, right now there is more energy at the sides than in the beginning. Okay, and if not, we can just run the random again, but it seems more. It seems like lower, and definitely the angles are not Gaussian. So it means that there is not a lot of correlation between these high frequencies in all of our sampling sets. And remember, our sampling set can be interesting. It can be data from an experiment. So by eye, we eyeballed it, and we think that something slow is interesting here. We verified it by looking at the histogram of all of the different data points, and now we want to get rid of all the fast fluctuation. So before the lecture, I played with it a little bit, and I changed it to, I eliminated all the frequencies 3 and above, but originally it was 10. So let's look at the original. Okay, so I took only one sample from the FFT, and I zeroed all the frequencies from 10 till the end. Okay, this line will do it symmetrically to both symmetrical parts of the FFT, and now I'm doing a reverse FFT. And the blue line was the original samples that we had. Okay, here we can barely see the original signal, right, which was a Henning window. Henning window is something like this. And the green line is it's what we got after we eliminated all the frequencies that are higher than 10. Okay? Yes?
In this chart, what is the reason for removing the high frequencies? I didn't understand the case that you looked at the histogram of the low frequencies and you saw that it's distributed normally.
Okay.
And
Gaussian.
for the high frequencies, so
Yes.
doesn't. But I don't understand why this means that there is something there.
So nothing really means, or it's not a proof for anything. But usually when we are looking at data, exactly as we did yesterday, we need to imagine something. Yes, if there are spikes or if there is any shape So if we cannot see anything, then we need to work hard. If we can see something, so we can test it. So we saw something that looked like humming window. Okay, we saw that when we averaged a lot of different samples, it's beginning to look like a certain shape. And the shape was really slow waves that came up and came down. And then all I did is to take FFT for each of these samples. Okay? And we looked at the FFTs of all of the samples that we've got. And we looked at the distribution of the lowest frequency. The lowest frequency represents what we actually saw. Okay? And it seems like most of the samples that we've got indeed has a lot of energy in the lowest in the lowest frequency, sorry, and also that they all had the same phase.
How did you define what's a low frequency?
So low frequency, we saw by eye that it is doing something that looks like one cycle. Okay, 1, 2 cycles, because it's not perfect cycle as before. So now, because we saw the example of 12 and a half cycles, we know that we're going to have some energy at low energy frequencies, not at whole frequencies. Okay, so because we don't have exactly 1 or 2 cycles, two whole cycles of nice sine waves, we got data that we can see that it started at some point. At the end of our sampling point, it finished one round of something. Okay? That's the reason why we can think there is energy at the low part of the spectrum. Okay? I just tested for 2. I could have tested for 3 or 1 or 4, but 2 seems like a nice idea to start with. And moreover, not only we saw a lot of energy at this frequency component at all of the different samples, we saw that they are all with the same phase. So that gives us a very nice intuitive way of thinking about it, that they all start at the same phase, which is not trivial at all.
When did you see that they have a lot of energy? We saw you showed us a normal distribution of the secondary phase.
So this is the signal.
Here you imagine a wave, like slow wave.
Yes. Okay, I can. Yes, you can definitely see that it's going up and down. Okay.
Yeah, but there's many.
Of course, there are many. Yeah, but when we average many times, only then we can see it. I already know that there is a certain shape because I did it. So of course I have a better hint. But usually we can see other shapes that can be very well described by eye. Okay, but here I think it's not supposed to be very difficult. The thing is that we see something that look like has some energy. If we can see it, so we can start looking at the FFTs of all of them. Maybe we'll see it in the FFT of all of them. But now we just look at the histogram of the lower part of the FFT to check for some correlation, and we did find a lot of correlation in the energy, and in even more correlation in the frequency.
How did you see correlation in the
Okay,
explain?
בטח. So this is the histogram of the energy in the lower frequency. Okay.
Only frequency number.
Yes, only for frequency number 2.
Okay.
Okay.
So what is the x-axis?
So the x-axis will be the value, the amount of energy. Okay. And the y is the number of samples.
Which x-axis corresponds to 2?
The amount of energy in frequency number 2.
Frequency, yeah.
Okay. I think what's more convincing is looking at the phases.
For everything.
The phases are much more convincing because you can see that it's much higher correlated. It says that in frequency number 2, most of the samples are, so this sine wave is started with the same frequency, and when we went to higher frequencies, okay, so there is some power but less power. Okay, we can see it in the distribution. The distribution is between 0 to 10, and the distribution of powers in frequencies 2 is much higher. It's around 30, 25. and the phases of frequency number 15 is totally uncorrelated. So these are all our hints. And
Phases are correlated, what does it mean?
it means that our shape, so we have many repetition of our data, and it seems by eye there is some shape, and we actually saw that when we're looking at frequency number 2, that inside our data, in all of them, this frequency started with the same phase. So it means that there is a process underlying the mechanism that created our data set that has some statistical properties. And in our case, it's the phase of the frequency of number 2 sine wave. But it's much easier. Okay, let's say we have some spikes, and we can calculate the statistical properties or the rate of them, and we just want to eliminate higher order frequencies. So this is exactly what we did here. Here, the spikes were extremely easy to look at because it was a sine wave, okay? Or almost a sine wave. And now, I just want to finish with the example of I'm going to zero all the other frequencies and see what happens. So this is what happens on one sample when I zeroed all the frequencies above 10. This is what will happen if I do it to all of the samples. Okay? So now we can compare the original signal, which looks like this, which is the, okay? So this was the original. So this is what happened when I eliminated all the frequencies above 10. Okay? So here it's definitely nicer than this. Okay? But still we can see that there is other fluctuating stuff. And at that point, what you can do to repeat the same algorithm. So here I eliminated all the frequencies that were 10 and above. And then I try to play with it and change the number of frequencies that I want to eliminate. Let's eliminate everything that is 3 and above or 4 and above. Okay, and now we get a really nice signal here. Okay, so this is really close to the signal that we started with, or the signal that we want to end with. Now, what I want to mention also that maybe it seems weird for now, but there are many ways to measure electrophysiological data, and many times it can look like this. Okay, if we do a single unit or multi-unit activity, this could be the data. And only if we have some knowledge about the we need some sort of knowledge. We can average a lot of time as something that looks like shape, and maybe can understand some of the frequency component on it. Or maybe we can look at a lot of FFTs of this signal. Yesterday I showed you that you can actually average a lot of time points from the data by the stimulus. So we have event trigger averaging. So we're going to average a lot of times after a stimuli, look at the shape of what we'll get, and if it's a single unit, maybe we'll see short waves of LSP, so it has a low frequency component. And maybe we will see some spikes in it, so it will have some high frequency inside it. Then we can average all the frequency component. We can do whatever, exactly the same thing that I did now, to eliminate all different frequencies and to get the real data that we actually want, which is great for us. Okay. Okay, another topic, small topic, because we don't have a lot of time, will be the time domain distortion because of filtering. to look at the FFT of this signal. So again, I'm going to look at the histogram of all the frequencies. Sorry, the histogram of all the FFTs, the real part of the FFTs from many different signals. So this is the amplitude of the frequencies, which is quite low. This is the angle. Okay. And this is the signal that we created. It was a spike in time 40 with some noise. And this is actually what happened when we filtered all the frequencies that were 30 and above. Okay. And yes, and we can see that some strange things started to happen. So first of all, we can see that the amplitude of the clip is lower. Well, this might be intuitively because we just took out some of the energy, right? We took out actually a lot of the energy. And we see that we added a lot of noise in the signal. Okay, so actually by filtering, we changed a lot of other properties of the signal that didn't happen in the first example. Now, all the filters that I did till now were, okay, I'm gonna get to it in a few minutes. Let's look at another example. Now, one of the ways to fight this phenomenon, so let's do it again, sorry. I created the signal, which is not interesting. I filtered the signal, so we got a spike here and a lot of disorder here around the signal. What people are usually doing, so now we're gonna look at the edges of our signal. So till now, in the first example, the spike was in the center. Okay? And here we can see that we added a lot of edges effects. Okay, so the noise that we added after filtering, we can see that there's a large stuff here and a large stuff also here. And one of the ways to try to eliminate all of these added noise that we don't really want is to zero pad this signal. Take this signal to make it extra long. I'm just putting a lot of zeros. So all of the zeros are in the beginning. So now it's twice as long as it was before. And now I'm going to filter it. Okay, so we see that most of the stuff that bothered us before are now at that blue part, or the non-interesting part. Now we can cut it back, okay, or just zoom in to the original data. And now we can see that if this was the original part that we were interested in, after filtering, now we have a much less disorder effect in the new signal. Yes.
When you do zero padding, you add information. Right?
Yes.
Information.
What information am I adding?
You add zeros.
Yes. So then zero energy. In all the frequencies, I'm adding zero energy.
Then your signal is longer, right?
Yes. The disadvantage of this method is that I'm making the signal longer, the FFT longer, everything is longer, but I can get rid of some of the edges effect that we got.
So what's the goal of this? To have better resolution or to the
So
FFT?
better resolution is a great idea, but we're not saying it's exactly here. Here we saw that one method of how to eliminate all the effect that we add on the edges. So that's a very famous thing that people are doing, and a lot of algorithms are using it. Okay, we ran out of time, but I think
for tomorrow, we're going to discuss a little bit about some problems about filtering large windows or large data, and sometimes people are padding for some other reasons. Just to give you some teasers, I think one of the interesting stuff that we can start to think of about them was that yesterday we took a data and we wanted to check only the high fluctuation rate. And the way that we did it was to smooth the data, right? We averaged each time point, and we actually got rid of some of the frequency content of the signal. So maybe we can talk about it in a mathematical way. We did convolution in the time domain. Okay, we did some function, right? It was averaged with some window on the time domain, but it clearly affected directly the filter that we're doing in frequency domain. And tomorrow, I'm going to show you, in my mind, it's the magical stuff that there is a one-to-one correlation or one-to-one function between the filtering that we can do in the frequency domain, the stuff that we can do in the time domain. Okay? So we will see that convoluting with different windows in the time domain is exactly the same as the whole process that we just did. Okay? So we did SSP, we eliminated some of the frequencies by just multiplying their entries by 0, and then we reconstructed the signal, and it's exactly the same thing as convoluting with the time window in the time domain. Okay, which is very, very practical in many, many things. Okay, so for today, I think that it will be nice for you to play with some of the examples, to get familiar with some of the examples from the SSP, from maybe creating new sine waves, maybe creating different data and just run your data or your imaginary data with the Fourier transform and think about the result. Look at the real part of the data, the imaginary part of the data, the absolute value of it. Try to take different windows and see what will be the effect, or try to think of what will be the effect. Just to remind you again that the length of the x-axis is exactly the same as the window, and it should tell you something about the resolution that you can get with an FSP. Okay, that's it.
למה זה? כי הרעש נוצר מהסוג שאני מסתובב בחצר, ואז יש לי
ואז
שהוא לא
יצרתי
עובד,
סטייט
כאילו
בודד
כאילו
ונשארתי עם
משהו
C,
כאילו
פחות
זה
אפילו
עובר אותה באופן
כן, אז
תמידי
כאן נשארתי
כאילו
עם C, בדיוק מה שאמרת עד כאן. כן,
זה ממשיך
אז בעצם אמרתי מספיק לרוץ עד C בגלל שיש איזה שינוי כן, זה מה שציינת בקצת.
בגלל שזה ממש בצורה הזאת. זה התשובה
כשמציבים את
מה
זה
קורה,
בבוקס עכשיו,
כאן ראינו
אז
שיש
כיתה גן,
מלא
אוקיי,
כאילו זה מה שאני מדברת גם, אבל באופן עקרוני אני לא מבינה
וגם אין בעיה, עכשיו שזה יעשה את כל ולא אכפת לי שזה יותר מזוקק. הרבה פעמים
ראינו שהפתרון נגיד,
גם בשביל וגם בשביל אם אני באמת רוצה לשחזר משהו שהיה כאן אני פני הפתאים, אני אשחזר ברזולוציה ויוריד אותם
אתה עכשיו אם פה השתמשנו בזה זה כמו מה שעשינו בקצת.
אנחנו לא משתמשים בזה סוגי.
לא, כי את אמרת שאם אנחנו רוצים לעשות סוגי כדי זה לא סוגי, אז נעשות לנו משולש.
כן, אבל אני באמת, עם משהו שבאמת לא מסתדר לי עדיין.
אני לא חושבת שזה כן יכול לעשות. הרגע מחקתי לי, תשכנע אותי, ואז תכנעתי חזרה.
איך הוא שכנע אותך? מה הוא אמר ששכנע אותך?
אבל נכון, גם לזה קראנו קורלציה. גם לזה קראנו קורלציה.
לדעתי זה קורלציה, ואני לא יודעת
לדעתי,
למה.
נכון, עשית את חד האנליטי?
עשיתי לא טוב, אבל עשיתי.
אוקיי, כולנו.
לא.
יש את החישוב של הווריאנט של y2, אז בתוכו מקבלים את החישוב של y. פשוט כאילו היה שווה קצת קורלציה, וחשבתי זה כמו שמחשבים קורלציה, כמו שיונתן נתן בכיתה. זה מה שלא קרה. וחגי אומר שזה לא הקורלציה. ואז הייתי אוקיי, חושבת שזה קורלציה, ופשוט לפתח.
אבל אולי אני צריכה איזשהו
רגע,
טיעון.
חישבת את זה כדי להכניס את זה פה, כדי
כן,
שזה לבד.
כן, וזה יצא לי באמת כמו שיצא בכיתה, בלי כל מיני שטויות שהיה לו שם, אמרו לקרוא.
זה בדיוק כמו מה שהוא נותן בתרגיל, זה עצמו נותן.
כן?
אז זה כאילו נכון, וגם מבחינה עדינית לא הבנתי מה הסימן של חגי. שכאילו, בגלל ש...
הנה חגי, בדיוק רציתי פשוט...
רגע, אבל כאילו...
אני חושבת שזה הקורלציה.
יש לי שאלה, אבל בתרגיל אמרתי לך שכאילו ידעתי שלא צריך לחשב את הקורלציה, נכון?
נכון.
אבל כאילו צריך לחשב את
זה
הקורלציה.
חשב
וואי,
אבל
זה קל.
פחות מגיע. זה להיות מפתח.
עשינו את זה בכיתה,
למה תקראת שזה לא הקורלציה הדבר הזה?
כאילו לא הבנתי, כאילו...
וליאור למדה מתמטיקה
די, זה לא נותן לי.
לא, רגע, אבל...
אני לא נותן דבר
אבל
בזה.
שוב, אם את רוצה את זה, אז אתה מחשב את זה.
נכון, אבל זה פחות מגיע מחשב את זה.
אמרתי את רוצה את הווריאנט.
לא, אבל אמרתי שקיבלתי את הביטוי הזה, לא אמרתי שהביטוי הזה הוא לא קורלציה, שחשבתי אותו y של t, y של t ועוד דלתה, אמרתי שזה לא נכון. אני חשבתי אותו פעם.
יכול להיות שזה כן נכון, לא קראתי לעומק, אני רק יודע שלעשות את הדבר הזה זה כמו לעשות מה שעושה, פשוט להציב עץ אחרת, מה שעשית.
נכון, אבל אתה הצעת פה t פריים ו-t פריים ו-t תגיים, ואני הצעתי פה t ועוד דלתה, ואמרת לי שזה לא נכון. קודם אמרת לי שזה לא נכון.
אמרתי שאני לא יודע. אז אוקיי, לא יודע. אם עכשיו
כי
הייתי...
זה יכול להיות כל דבר,
אז אם הייתי אומר לך לחשב את הקורלציה עכשיו של y,
זה הקורלציה של y.
הייתה יותר קצר?
וזה גם מה שקיבלנו.
כמו הווריאנט?
לא, זה לא